Thanks, Keith. I'm Dr. Zach Kabelac. I spent 11 years at MIT as an electrical engineer studying radios, radar systems, and analytics. And previous company was radar for healthcare, but now it's a radar in space for agriculture and climate applications. And so my company that I founded a couple of years ago, Aperture Space, is developing a payload and analytics for novel radio sensing for Earth health monitoring and critical intelligence. So this should be pretty familiar to you, many of you in the crowd, but imagine you're a North Dakota grower. You've planted corn seed about 10 weeks ago, and you know that that crop is getting to a critical growth cycle in its development and is already a couple feet tall, but is extremely sensitive to both water and nutrients. It rained yesterday, and it's expected to be hot over the next week or two. And you have to ask yourself, how much and when am I going to irrigate, and what prescription of fertilizer am I going to apply in which field to work? Now, that's really so when you ask yourself, you say, well, traditional wisdom. But given the world we're in today, is traditional wisdom enough anymore? And that's really the question that you have to ask yourself. It's the million-dollar question, and across the country, many other farmers are asking the same thing. Is that enough? It's a billion-dollar question. Now imagine you're across the Atlantic. You're Laura. You're in an early morning train going from Birmingham to London. You've got an important meeting tomorrow, and you have a flight in a few hours to catch. The PA system on the train indicates that, alerts you that the train's been stopped because of a landslide collapse on the tracks shortly ahead. And as you look out across the field, you see that you're in acres and acres of nothing, and you're going to miss your train. Despite the fact that both Jeff and Laura are thousands of miles apart, they have one thing in common, and that's actually soil moisture. Soil moisture is used for many key farming decisions today, and it's also one of two predictors for landslides. You might think, soil moisture is such a fundamental metric, isn't it already measured by NASA, NOAA, USDA, USGS, whoever? And the answer is yes, it is, but it's too low resolution to be used by me and you. The data and the soil moisture that they produce is used for cities, states, nations, regions to make policy decisions at the community level. And so for us as individual actors and businesses, that data is actually quite impractical. There are a few other companies that exist to produce soil moisture, but those businesses are largely doing it for numerical weather prediction. And weather doesn't need to know soil moisture at the acre level. It needs it at the kilometer level. And so what we need is a high-resolution soil moisture map that can imply individual action on fields and zones and acres rather than counties and states. Now, soil moisture is actually a very difficult problem. The obvious, easiest way to do it is with in-ground sensors. But every time you want a measurement, you have to go out to the field to install it after planting, and you have to pick it up before harvest. They're both cumbersome, and you can lose connectivity and data loss, and they really only tell you about the data within the soil moisture within 10 to 15 feet of where it's planted. Most of the satellites on orbit use optical imagery, just like akin to a cell phone camera or a DSLR. And so when they're not blocked by clouds 30 to 40% of the time, they're essentially looking at sunlight reflection off of the plants. And so they're only seeing the leaves turn brown after the soil moisture has been dry for a few days or a week. There are a couple of civil satellites that measure soil moisture, but they're either extremely expensive, low resolution, or low revisit rate. And I promise you I've tried all of these solutions first. And so this is where my company Aperture Space comes in. We're developing a low-frequency radio sensor that is extremely sensitive to soil moisture, as well as a scalable analytics product that combines data from multiple satellites including a soon-to-launch NASA NICAR satellite next spring. In the long term, we hope to have our own satellites on orbit producing this data with higher accuracy and a more frequent revisit rate. This data, we combine the satellite imagery with soil maps, topology, elevation, weather data, and more. And we fuse it through a hydrological modeling that combines machine learning and hydrological physics-based modeling to produce a very simple and clean soil moisture map at 30-meter resolution. That's really just a 0 to 1. Is it wet or is it dry? All of this gets distributed through a simple web app API that can task the system and return data in a clean fashion. So what makes low-frequency radar special? At the heart of it, it's the wavelength. Now, these images are definitely not to scale, but essentially our radar is what's called L-band at roughly 1 gigahertz. If you're familiar with the space industry, the most common radar or synthetic aperture radar, Umbra, Capella, ICEYE, and others, is at X-band at 10 gigahertz. And so really what that means at the end of the day is a difference in wavelength between the signal that's transmitted. Now, from why this matters, from simple electromagnetics, the longer the wavelength, the deeper it can penetrate through a medium. So all of those X-band SAR satellites that operate today are radiating the Earth with these high-frequency radio signals, but they're reflecting off of leaves and tree canopies and topsoil. Whereas L-band, on the other hand, given the longer wavelength, is able to penetrate through the medium into the soil and reflect because of the soil moisture. But where does the measurement of soil moisture come into this? So again, from electromagnetics, as the signal propagates through air, the dielectric constant of air is 1. That's the baseline. The dielectric constant of dry soil is 4 to 8. And so as the signal propagates through air and reaches that transition from air to soil, it reflects some of the signal while the rest of it penetrates into the ground. But the dielectric constant of water is 80. And so the more water there is in the soil, it raises the aggregate dielectric constant, making the signal more reflective. So in dry soil, the signal reflects less, and in wet and inundated soil, the signal reflects much more. And that's how a radar satellite from space can measure such a sensitive thing beneath the surface soil, where it's just some simple fundamental physics. And so soil moisture itself, as I've come to learn as a technologist, is reliant for many industries, and particularly agriculture. Obviously, there's the act of farming itself for irrigation and fertilizer application, as well as crop yield and crop yield prediction, and even simply farm operations. Is my field too muddy to drive out to today? But it relates to an entire ecosystem that ultimately is centered around the farm as a productive economic unit. And so you have the farmer itself who's working the land, but helping them directly are your OpEx providers, your seed and your fertilizer companies. You have your CapEx, which is your machinery and equipment, all of which want to know how well their stuff is working on the land. But then tangential to them, you have your crop insurers, possibly your landowners. You have other supportive agronomists and businesses like Aperture Space and others who also care about the productivity of that land. And then sitting off of them, at the largest scale, you might have your commodity traders, your county, state, and national governments setting policy based on the productivity of the region. But at the end of the day, all of these parties care about how that land is producing and making it more efficient. The data soil moisture obviously will play a role with water management. The US and Europe move over 100 trillion gallons of water every year. And me coming from Boston, we actually lose about 40% of that water from the processing plant to its end use. And so it costs a huge amount of money through these subterranean underground losses. And lastly, there's a big climate mitigation relationship where soil moisture is extremely useful for wildfire prediction, landslides, which I talked about earlier, droughts, and even flash flooding. And if any of you are related to carbon markets, modeling soil carbon is highly dependent on soil moisture and soil conditions. And so we believe that the laws of physics really favor Aperture. Many people think there are prevalent methods today that accurately measure root zone soil moisture, that results from radio signals are comparable to other alternatives, and that businesses can easily work with these radio signals. But they're all myths. The fact is, there's only thing that can truly penetrate topsoil is low-frequency radio signals. All other methods are either surrogates or at best proxies, and most businesses lack the technical expertise to work with these. And so our expertise at Aperture Space to work with these complex radio signals and distill them down to simple, usable soil moisture maps is our advantage. So with that, thank you for your time.